Okay, so now we're ready to put things together. So there's a few formulas that I will want to use. So let me just record them over here. So the first one was the beta function was 3g bar squared over 16 pi squared. And this was equal to minus m dg bar dm. And we calculated this in 4 dimensions. That was the running coupling, the equation that the running coupling obeyed. Then we have just calculated the dimensions of G. We called it G epsilon. And this is length to the minus epsilon if we are in D is equal to 4 minus epsilon dimensions. Okay, so what I'm going to do is I am going to set G tilde to be equal to M to the epsilon multiplied by G bar. Okay, and what's going on in this formula? Well, that M to the epsilon has got length dimension L to the minus epsilon. So by writing G tilde in this way, we know that G bar is dimensionless. G bar is length to the naught. This beta function over here, G bar is equal to L to the naught, and this was worked out in D is equal to 4. So this is how in D is equal to 4, the coupling changed as a consequence of interactions. Now, we're working in 4 minus epsilon dimensions, so we're close to 4 dimensions. I'm going to imagine that G tilde is M to the epsilon, so that M to the epsilon is going to produce some change in the value of the coupling as I change the scale, just because it's dimensionful, times by G bar. And G bar will change to excellent approximation in the way that it changed in the 4-dimensional theory, because we're very close to 4 dimensions. So with that insight, let's work out what is the beta function for G tilde. So this will be minus M dg tilde dm. And there's two terms here. I could hit the M to the epsilon, or I could hit the G bar. Now, when I hit the M to the epsilon, what do I get? I will get minus epsilon M to the epsilon G bar. And then when I hit the G bar, well, we said that the way interactions affect G bar is going to be just as it was in 4 dimensions, because we're very close to 4 dimensions. So in that case, we will have the beta function, 3 G bar squared over 16 pi squared. This is what we get from applying minus m d by dm to G bar. And then we just need to multiply by m to the epsilon. So in this beta function, what's happening? So this term over here is trying to make the coupling grow. And why is the coupling trying to grow now? The coupling is trying to grow because it has a negative length dimension. And this term over here is trying to make the coupling die or decrease. Okay. And why is it trying to make the coupling decrease? Because that's what interactions do. The interactions tend to make the coupling irrelevant. What we're going to do now is we're going to try to balance exactly these two effects by setting this beta function equal to 0. So if we set this beta function equal to 0, what's the equation? Well, we can cancel off the m to the epsilon, that's common to both terms. We can cancel off a g bar that's common to both terms. So then we get epsilon is equal to, it is 3. There is a g bar after we've cancelled one g bar over 16 pi squared. So we now learn that we should set G bar equal to 16 pi squared over 3 times by epsilon. So if we're very close to 4 dimensions, we only need a very, very weak coupling, and we get a nice conformal field theory. Now here we often put a star next to this G bar, and this is often called the critical coupling. Critical coupling. So this is the coupling at which the beta function actually vanishes and we get a conformal field theory. So just to stress again the logic, what we found in our 5-4 theory, we found that interactions tend to make the coupling irrelevant. So we said that the coupling is marginally irrelevant. So interactions decrease the coupling. When we go to slightly less than 4 dimensions, the coupling now gets a negative length dimension. So just the dimensional analysis effect of changing scales is going to cause the coupling to grow. And to get a CFT, we've exactly balanced those two effects so that in the end, the coupling remains absolutely fixed. It doesn't change at all. The beta function vanishes and we have a CFT. Now, what people do is they do this systematically. So you can work in 4 minus epsilon dimensions, evaluate all of your Feynman diagrams in 4 minus epsilon dimensions, and do a really honest calculation of the beta function to any loop that you like. And you can see that epsilon both tells us how far away we are from 4 dimensions, and it tells us the size of the coupling through G bar star being proportional to epsilon. So you can do perturbation theory in epsilon. You can do it to any loop order you like, and you can calculate any quantity you're interested in to any order in epsilon. So people do this to remarkably high order in epsilon, and they even try to get accurate approximations to the theory at epsilon is equal to 1. Now, at epsilon is equal to 1, 4 minus epsilon is equal to 3, and you're actually working with a 3-dimensional system. And there are many 3-dimensional systems that you can realize in the lab. You can calculate their critical exponents, all of those different scaling laws that you would find for the CFT, and those can be compared to experiment. And actually, this is a remarkably successful exercise. It's well-defined CFT that makes predictions that are in very good agreement with what you measure in the lab. Okay, so enough about the Wilson-Fisher fixed point. By the way, there's Wilson-Fisher fixed points in other dimensions using different theories. For example, in 6 dimensions, you can find a Wilson-Fisher fixed point for the phi cubed theory. And instead of going slightly below 6 dimensions, in that case, you go slightly above 6 dimensions, but you can also define a CFT. So this logic you can use in many different places. Another very common CFT that people study is called the Bank-Zaks fixed point, and that's what we're going to study next.